So what we have here is a 1.4 kilogram block that slides down a frictionless incline at an angle of 20 degrees with the horizontal. As it slides from point A to point B, a force P with magnitude of 30 Newton acts on it along the slope as it's shown on the diagram. The kinetic energy at point A is given to be 42 joules. The question here will be, what will be the kinetic energy at point B if we know the distance between the 2 points A and B to be 7 meters? We will be calculating potential energy, and so as preliminary steps we will need to set up our ground. A natural choice will be at the lowest position, that is point B. Here I'll set up my y to be 0. Then the question will be, well, what is the original height from which the block starts? That is the height of point A. I don't know that height, but I recognize here a right angle triangle for which the y and L are the two sides of that triangle. The y is the opposite side to the angle theta and L is the hypotenuse, so I can use the definition of sine here. I will have the opposite side y over the hypotenuse L has to be equal to sine 20 degrees. That gives me for y to be equal to L sine theta. So here I have a choice. I can keep the expression as is with symbols for now, or I can actually plug in the numerical value for L and see that the block starts at location A at about 2.39414 meters. Just a brief comment here about the number of digits. In physics, there are usually two situations in which we are mindful of how many digits we keep. One situation is when we're using numerical values that come as measurements from a lab, simply because in the lab the number of digits is dependent on the precision of the instruments that we use. So if we have expensive instruments with high precision, we'll keep more significant digits. The other case, since this is a problem and we don't know what the instruments were used and we have no idea what we did in the lab, presumably to do those measurements. The second situation in which we actually have to be mindful of the number of digits that we keep are if we actually plug the numerical values too early in our solution of the problem, because sometimes we can actually accumulate a rounding error, which is clearly the case here. I haven't even started solving the problem, and here I did figure out what the height y is. So this is the reason why I actually have decided to keep extra digits. Normally I would write 3 digits, maybe sometimes 4, but in this case you can see that I have 6 significant digits. So now let's go back to the solution of the problem. Let's look at the total mechanical energy at point A. Kinetic plus gravitational potential will give me 42 joules according to the problem. That is the kinetic energy at point A, plus mgy, that's the expression for the potential energy. I just calculated what y here is. That's L sine theta or sine 20. So I can write 42 joules plus mgl sine 20. Here we can also plug in again the numeric values for the mass in g. So I'm going to have 42 joules plus 1.4 kilograms for the mass of the block, 9.8 meters per second squared for the gravitational acceleration, and the result for the y, which I have from above, 2.39414 meters. So it looks like the energy, the total mechanical energy at point A will be 74.848 joules. Now let's look at the total mechanical energy at the bottom. Kinetic plus gravitational potential energy gives me the kinetic energy at the bottom at point B, which is the question in this problem, plus mgy. Of course, that is where I placed my ground or level y 0. So that means by virtue of my choice, the potential energy there will be 0. So I see that the total mechanical energy at point B depends entirely only on the kinetic energy of the block. So applying here the work energy relation or theorem, we know that the change in energy, the difference between the final and the energy with which I started at point A, will be due to the effect of the non-conservative forces. In this problem we don't have friction, but we do have force P, which is non-conservative. Remember, in mechanics, in a realistic everyday scenario, there are only two forces that you need to consider as conservative: the gravitational force and the elastic force of a spring. Everything else in the problem will be non-conservative force, and we do need to be mindful of the work that that force might do. So here, let me write it in terms of the difference in the energies. The final energy, which is the energy at point B, minus the initial energy, that is the energy at point A, has to be equal to the work of that non-conservative force, which is the force P. So naturally, the question here is, well, what is the work of that force? We'll use the formula for a force that is constant and doesn't change its direction. The work of such a force will be simply equal to the force times the displacement as the block moves, times the cosine of the angle between the force, the applied force, and the displacement. In this case, the displacement is down the slope, and so is the force P. So the parallel, in other words, the angle between them is 0, and I have written it here as cosine of 0. So that expression actually numerically will be 30 newtons times 7 meters times cosine of 0, which is 1, and ultimately the work of the force P is 210 joules. With that, I can actually go back to the work-energy relation, and now I can start putting the numbers for the energy and for the work. First, the energy at point B, remember, was equal simply to the kinetic energy at point B. Then I have to subtract the energy, what I had at point A, which was 74.848 joules, and that had to be equal to the work done by the non-conservative force P, 210 joules. And here what is left is simply to calculate the kinetic energy at point B, which comes out to 285 joules. Notice here that I rounded everything down to my standard 3 significant digits because this is my final answer, so I don't need to worry about rounding off error anymore.